13.6, it says I can calculate the total heat of a system going through both a phase change and a thermal change. So the fact that it says it's the total heat here means that I have to add something up. And it tells me I'm going to do a phase change, which we know is going to be a stoichiometry calculation, and a thermal change, which is going to be Q is equal to mass times Cp times delta T. Okay. Now, in this problem, you've been given a lot of really important information. First of all, is you just quick scan. I see I'm working with acetone again, so that's going to be important when we go back to our table. And it says how much energy would be released, so that's kind of important also. That means energy is being given off, so we're probably going to have negative values. And then we have a mass, and then we have an initial temperature, and it's cooled to being frozen. So that tells me that what's really happening here is I'm starting as a liquid at 45.2 degrees Celsius, going to freeze, and we'll look up that temperature in a second. So I'm going to go back up here and find that. Acetone's freezing point and melting point is negative 94.9. So at negative 94.9 degrees Celsius. And then I'm going to be solid, because it's frozen, at negative 98.6 degrees Celsius. So I'm just going to use that to help me try to decide what to do when. But I do know that I have to take this acetone and cool it from 45 to its freezing point. So that's going to be my first calculation. So that's going to be Q, mass, specific heat, and change in temperature, which is TF minus TI. So my mass is 24 grams. My initial temperature here is 45, but my final temperature here is going to be the freezing point, so negative 94. So I'm going to have negative 94.9 degrees Celsius minus 45.2 degrees Celsius. And now I need to go find my CP, and if it's a liquid, I need to find the CP of acetone as a liquid. So my specific heat for acetone as a liquid is going to be 2.22 joules per gram per degree Celsius. So I'm going to put that right here. Okay, now, so now I'm just going to use my heat formula, which is Q is equal to mass times Cp times delta T. So Q is equal to the mass, which is 24.0 grams, times the specific heat at a liquid, which is 2.22 joules per gram per degree Celsius, times the change in temperature, which is negative 94.9 minus 45.2 degrees Celsius. And when I plug that into my calculator, I get a value of negative 7,464.528 joules, which I'm going to convert right away to kilojoules. So we know that 1 kilojoule is equal to 1,000 joules. So that's negative 7.4, let's say 6, because of the 3 sig figs, kilojoules. So that's going to be my first calculation here. My second calculation, because the problem actually dictated it, is going to be a phase change. And my phase change, remember, is going to be a stoichiometry calculation. So I'm going to take, so that goes, again, mass to mole to energy. So I'm going to take the mass, which is 24.0 grams of acetone, C3, H6O, put it over 1. And then I'm going to go to moles, and then I'm going to go to energy. Now, in this problem, I've already calculated the molar mass of acetone from up above, so I'm just going to kind of remember that the molar mass of acetone is 58.9. So I'm going to put that right here, 58.09 grams of C3H6O in 1 mole. Now, if we're going from liquid to freezing, that tells me that I need to use a delta H value, and I'm going to use the delta H of fusion because the delta H of fusion is when we freeze or melt something, and that's 0.569. So I'm going to write that down. So we're freezing. So we need to find the melting point, freezing point, which in this case is the 5.69 kilojoules in 1 mole. So I'm going to put the 5.69 kilojoules here and 1 mole on the bottom. And then I'm going to go back up and just look at this little ditty right here at the top that says heat added is endothermic, delta H is negative. Heat being released is exothermic, delta H is positive. So in this instance, because heat is being released, we're going to say that this is going to be negative. And so now we're going to multiply straight across. So 24.0 divided by 58 times negative 5.69, I get a value of negative 2.35 kilojoules. Okay. And then lastly, we have to do one more calculation here. And I'm kind of sort of running out of room. I should have done that differently. One more calculation here. So now we're going to calculate because now that it's frozen at negative 94.9, we are going to go ahead and calculate how much energy is needed to make it get to negative 98.6. So that's going to be Q. Mass is still 24.0 grams. The CP now will be slightly different, but the delta T is going to be the final temperature, which is going to be negative 98.6 degrees Celsius, minus its initial temperature, which is the freezing point. So this is going to be my TF. This is going to be my TI. And the CP this time is now it went from a liquid to become a solid, so I need to find the correct CP. So I'm going to use the CP this time, which is 1.65 joules per gram per degree Celsius. So that would be 1.65 joules per gram per degree Celsius. So now I'm going to use my formula, which is mass times CP times delta T, or 24 grams times 1.65 joules per gram per degree Celsius times the negative 98.6 degrees Celsius minus negative 94.9 degrees Celsius. And that's going to give me a heat value of, I'm going to put this right down here, negative 146.52 joules. And again, I'm going to convert that right away to kilojoules because that's the currency of energy in chemistry. So that's 1 kilojoule in 1,000 joules. And so that becomes negative 0.14, let's say 7 kilojoules. And then the last thing that we have to do, which I realize I'm running out of room just a little bit, is we have to add these things up. So I have so I'm going to do it down here. I have negative 7.46 kilojoules plus negative 2.35 kilojoules plus negative 0.147 kilojoules. And when I add all of that up, I get a value with the appropriate number of sig figs to be 9.96 kilojoules of energy present. Questions about that?